So today we are going to talk about the homework of chapter 2. Okay, so first we want to look at the problem 2.1. So in this question, we look at the point charge Q, which is located at a distance d away from the infinity plane conductor, hold at zero potential. Okay, so here we use the image charge to calculate the potential first. So we can easily show that the potential is equals to this term, which z direction is as this. Okay. And under condition to show that when z is z is bigger than 0, the potential is will fit the boundary condition. Okay. Then for power A, we want to calculate the surface charge density. So as we have the potential, then we can easily calculate the surface charge density as this formula. So we take the derivative of potential over z and substitute the z to 0 to get a surface charge density on the plane. Okay, so we can just do the calculation and get the result as this. Okay. Then for the problem B, we want to calculate the force between plane and charge. Okay, and as we read from the image charge theory, then we can know that the force between plane and the charge Q is equals to the force between Q and its image charge minus Q. Okay, so we can simply calculate the force between these two as the Coulomb's law. Then we can get the results this term. Force. Okay. And for the problem C, we want to calculate the total force by integral this force density. Okay, let's do like force density. Okay, so we just integral this term. So here we substitute the surface charge density as we calculate in the problem A. Then we just do the integration in the cylindrical coordinate. Then we can get the result as this term, which is the same as we use the same as the result in the problem B. We use theory. Okay. And then for the problem D, we want to calculate the force to the work necessary to remove the charge from this position to the infinity. Okay, so we just simply integral the f from distance d to infinity. Okay, then we just calculate the integration, and we can get the results this term. Okay, for the problem E, then we calculate the potential energy between charge Q and its image charge. Then we just calculate it and get the result this term. Okay, very easy. Then we will find that the work necessary to remove the charge Q from this position to the infinity is equals to potential energy between charge Q and this image charge. Okay, this is because the potential energy of these two is not equal to the work, because actually there's no image charge in reality. So in this region, actually the field is equals to 0. Okay. So here we just over calculate the entry of image charge area. So you will find the difference between these two. And for the final problem F, okay, we just simply put the charge in one angstrom from the surface and derive it in the electron volts. Okay, so it's this here. Then for problem 2.2, we want to calculate the potential inside the surface as this. So for the bounded conducting surface, we just look at the portion as the Q in the inside and the image charge Q in the outside of the surface, which is very similar to the problem 2.2. Very similar to the 2.2 in the lecture note. Okay, in the lecture note. So by substitute the sorry, just by fit the boundary condition, you can easily get the y prime. Y prime is equals to this term, and q prime is equals to this term. Okay, you can check by yourself. Just apply the boundary condition as you do in the 2.2 in the lecture note. Okay. Then for problem B, we want to calculate the induced surface charge density. So as we do in the problem 2.1, we just use the formulas this term and to calculate the derivative of potential and get the final result. Okay. And for the problem C, we want to calculate the force on the Q. Okay, so we just use the Coulomb's law. Okay, so it's just the force between these two charges. And we can easily get force as this term. And for the problem D, we want to discuss that if the surface is kept at for fixed potential V, then we will find that the surface charge density is not changed. Okay, surface charge density and the force will not change because you just shifted the potential V, which is not. Oh, sorry. So yeah, you just simply shifted the potential. Okay, which will not affect the result of surface charge density and force. And if the surface has a total charge Q in its surface, then we will find that the inside surface will have a big Q minus Q, and the outside surface will have a big Q plus Q. Okay, so if you want to calculate the potential and or force or any other things, you just use this condition. Okay. So for the problem 2.3, okay. So here we have a straight line. Okay, linear charge density Q, linear charge density lambda, and total, which is the same as to Q in here. So as we know, the potential of the isolated line charge is equals to this term. So we just use the image charge to fit boundary condition. Okay, so we can know that the total potential will equals to this as we use this structure. Okay, because we want to fit the boundary condition these two these two. Okay. So potential at these two s's will equals to 0. Okay. So you can easily to check. You can easily to check the boundary condition as this. In the list two line, the boundary condition potential it will equals to 0. And so for the problem B, we still do the calculate the surface charge density. Okay, so by the same process, we just take the partial derivative and substitute y equals to 0 to get the final result. Okay, then in here, if we change the different S0 and Y0, then we can get a different surface charge density over rho or over lambda as this different plot. Okay. So for the problem C, we want to calculate the total charge density on the plane y equals 0 and x bigger than 0. Okay, so we just simply calculate the surface charge density we have in here, and integral is over all the surface. Okay. And we can just do the calculation and get the results this term. So for problem B, we want to find that if we look at the region where rho is bigger than the rho 0, then we will find that this for the default charge will look similar like a quadrupole. So we just calculate this question by use the potential we calculate above and by Taylor expansion. Then we leave only the lowest non-vanishing order to estimate widely, and we get the final potential as this term, which will the same as the quadrupole potential. If you can get that, okay. Then for problem 2.4, okay, so here we have a charge outside of the surface and have a total charge Q, big Q, we assume here. We have a total charge big Q on the surface. So by separating the problem as two questions, the first one is we have a charge Q outside the surface and for the grounded surface. Okay. And second question is the second part is the only total Q on the surface system. So by separating these two conditions, then we can get the potential as this term. Okay, you can easily to check that. Then for problem A, we want to calculate force on the potential charge Q. So we can easily show that we can drop the first term because we want to calculate the force on the charge Q. Point charge Q. Okay, and this term is the potential induced by charge Q himself. So we can drop this term. So and we we just calculate the force by derivative of the potential, a partial derivative of the potential. Then we can get the force. So if we want to calculate the position where the attractive force and the repel force were equals to each other, which means the total force F equals to 0, and say the big Q on the surface is equals to the small q, which is the point charge. Then this formula will lead to this equation, and you can just put this equation to the work frame, then get the answer as this term is the d over r is equals to 1.61803. Okay. Okay, then for the problem B, we want to calculate the force if the point charge is very close to the surface. So the D is equals to big R plus A, where A is very smaller than R. Okay, so we just put this condition on the force we calculate above this. So we put the condition in the force and we just expand it, and apply the condition where A is very small and very far smaller than big R. And we can find that in this limit, only the R with order of 5 term remain in the upside, and only the a squared times 4 times with the order of 5 remain in the downside. Okay, so the force will equal to this term, and here you will find that this term is is the same as the force we calculate in the previous problem, which is the force between a point charge and his image charge in the plane. Which means if you look close enough to the surface, you will feel like you are looking at the plane as well. And for the problem C, we want to calculate the total charge on the surface is twice or half of the point charge. Then as we calculate this, we just simply put the big Q equals to twice the point charge or the half the point charge, and do the calculation of these different equations and get these two answers. Like the same as before, you just put this. You just need to put this equation to the work frame and get the answer. Then for the problem 2.5, we want to show the work done to remove the okay, and by the force in the equation 2.6. Okay, so we just simply calculate the integration. So the total work is equals to force dy, where y is from R to the infinity. So we just simply calculate integration and get the result. And compared to the energy, compared to the potential energy between the charge, then you will get the potential energy is bigger than the work you need to remove the charge. the reason of this is the same as the problem we explained the 2.1. Okay, because the image charge is actually not exist. Okay, so you are over calculated the potential energy in this term. And for the problem B, it's calculated by the same process. You just calculate the work by integral the force from R to infinity, and you can calculate the potential energy between the charge simply this term. And this term you will find that they are still not the same because the same reason there's actually no image charge, so you cannot calculate the potential difference just simply by these two. Okay. So this is all about today's problems. So if you have any question, you can ask me after the class. Okay. Thank you.